And we're going to pivot to, we've seen the Bay now, we've seen the communities now, and we're going to pivot to the end of the century. And we have with us a scientist from the New Jersey, from Stevens Institute of Technology in Hoboken, New Jersey, Reza Marsooli, who is in the Department of Civil, Environmental, and Ocean Engineering at Stevens. He has a bachelor's degree and master's degree in civil engineering, and his PhD is in engineering science with a concentration on computational hydro science and engineering. And so he is going to give us a view of what we are going to see in Jamaica Bay communities as we head towards the end of the century. And so, Reza, thank you very much for coming, and we look forward to hearing from you. We are starting you off a little late, so that does not mean that you have to, we have a little flexibility in our program. We don't want to crowd you, just so that you know that. Okay.
Thank you very much, Richard, for the introduction. If you don't mind, let me please share my screen first. All right. Hope everyone can see my screen. I'm sharing my screen, and I think it's about exactly 12 o'clock at noon. So I don't know if I should say good afternoon or good morning, but hope everyone is well. My presentation, the title here is a little bit different from what you see in the agenda of the conference, and the difference comes from these two words here I added, flood hazards. The reason is that one main area of my research is the effects of climate change or sea level rise on flood hazards. So I thought it's relevant to talk about flood hazards as well. So the first part of the presentation, you'll see projections of sea level rise, and those results are coming from the Intergovernmental Panel on Climate Change. And the second part of presentation, which is about the effects of sea level rise on flood hazards, the results are directly from my research group at Stevens. So we're going to have two parts in this presentation. We're going to start with some introduction about sea level rise, what sea level rise is and what causes sea level rise. We're going to a little bit talk about global sea level rise and relative sea level rise, what they are and what the differences are. And then we're going to look at the impacts of sea level rise on Jamaica Bay and flood hazards in Jamaica Bay floodplains. With that, let's get started with a quick introduction about sea level rise. So this is a definition of sea level rise, which is an increase in the level of the world's ocean due to the effects of global warming. Here in this cartoon, I show the present. Let's assume that this level is the present day low tide in a specific location, and then we have present day high tide. So if I average them over a specific period of time, I get the mean sea level. So we have the present day mean sea level shown by this black line here. What happens in the future due to sea level rise is that the present day low tide is going to reach higher elevation. So with this dashed line, the yellow dashed line represents the future low tide elevation. Similarly, the present day high tide elevation is going to be higher. So high tides are going to reach higher elevation in coastal areas. And now if we average the future low and high tide, we get the future mean sea level. What are the impacts? What are the impacts of sea level rise? I think previous presentation, they talked a little bit about, or they talked about salt marshes, they talked about flooding and the impacts on coastal areas of Jamaica Bay. So here I just list a few examples of the impacts of sea level rise, which include erosion of beaches or salt marshes, more frequent and or intense flooding, permanent inundation, loss of marshes and wetlands, and saltwater intrusion. Now we're going to look at the definition of global sea level rise. What is global sea level rise? And then later in the next slide, we're going to see what is the difference of global sea level rise and local sea level rise. So global mean sea level rise is the average height of the entire ocean surface, which is caused primarily by the added water from melting land ice sheets and glaciers and the expansion of seawater as it warms. So when the water warms, its volume increases. So imagine the ocean is getting warmer, the volume increases, it means that the water level is increasing. We have sea level rise. And then we have also ice sheets which are melting. So as they melt, the water is entering the ocean. Again, the sea level in the ocean increases. So these are two primary causes of global mean sea level rise in the global ocean. This photo here shows Moore Glacier in Alaska, and the photo was taken in August 1941. This glacier is, you can see this white area represents the Moore Glacier, and then 60 years later, from the same region, the area, this picture was taken in August 2004. And it's obvious that the glacier, a large area of the glacier is gone within 60 years. I don't have any new recent picture, but I myself, I'm curious what happened now for the remaining part of this glacier. Now, the question is that how global sea level rise would look like in the future. So here, what we see on the x-axis of this figure is decade, from 2020 all the way to the end of century, 2100. And on the y-axis, we see the global mean sea level rise in feet. From this line, this blue line, I can say that projections show by the end of 21st century, we're going to have 1.3 feet of global sea level rise. And this number is for an optimistic scenario. And by optimistic scenario, I mean that 0 CO2 emissions will be achieved around the middle of the century. It means that in the middle of century, we won't have any, we reach 0 CO2 emissions, no fossil fuel anymore by the end mid-century, and we can achieve the climate policies. So this is the best climate scenario, the optimistic climate scenario. But even under this optimistic scenario, which is called SSP 1.9, we still get 1.3 feet of sea level rise by the end of century, and that has 50% chance to occur. 99% chance to get 0.5 feet of global sea level rise by the end of 21st century. 95% chance to get 0.7 feet. 5% chance to get 2.3 feet. And 1% chance to get 3.1 feet. So even under the best climate scenario, the most optimistic climate scenario, we still can get a sea level rise between 0.5 feet and 3.1 feet by the end of this century. And why we have different percentages? Because of uncertainties. I think it was mentioned in the previous presentation. Because of uncertainties in the climate, we also have uncertainties in the sea level rise, how much sea level rise we'll face in the future. And those are represented, the uncertainties are represented by these probabilities. What about the worst case scenario of climate? Let's say we won't be able to achieve our goal to reach 0 CO2 emission around the middle of century. Now I'm going to look at the worst case scenario and compare that with this best case scenario. The worst case scenario, it's called SSP 8.5, and these are the names which IPCC, the Intergovernmental Panel on Climate Change, assigns to these scenarios. Under this scenario, high reference scenario with no additional climate policy. It means that we won't have any climate policy. We just do the business as usual. That can be the worst case scenario. Under this SPC 8.5 scenario, with 50% chance, we get 2.5 feet of sea level rise by the end of 21st century. This is, remember, this is global sea level rise. It's average over the entire ocean. And compare 2.5 feet with 1.3 feet, almost 2 times. And the range is also wider. So we can get something between 1.56 feet and 5.5 feet by the end of 21st century. But the question is that, does everywhere get the same amount of sea level rise by the end of 21st century, or sea level rise is going to change from one place to another place? And the answer is yes, sea level rise is changing from one place to another place, and that's called relative sea level rise, which is how the height of the ocean rises or falls relative to the land at a particular location. So we already talked about global mean sea level rise. I have it here. So if I add the local effects, I get the relative sea level rise at a specific location, in our case, Jamaica Bay. We are interested in Jamaica Bay. So if we know global mean sea level rise, we know the local effects, we get the relative sea level rise. What are the local effects? Local effects are due to sea level fluctuations, ocean circulation, and vertical land motion. So ocean is not stationary, right? Ocean is circulating, and the circulation changes from season to season, year to year. So changes in ocean circulation can impact the mean sea level. And we have vertical motion of land. Vertical land motion, either sinking, which is called also subsidence, or uplifting, is due to glacial isostatic adjustment, tectonics, and groundwater withdrawal. I don't get into the details, too much science perhaps, but quickly to mention that what, for example, glacial isostatic adjustment means. So we know that ice sheets are heavy. There is a large mass of ice, and the weight of that large mass of ice is going to be tremendous. And what it causes is that ice mass depress land below. Here, this arrow down, it means that this area is pushed down and displaces nearby land upward, which is called for bulge. What happens if this ice sheet gone? So the land which was previously pushed down, now it's rebounding, and the land which was uplifting, now it's sinking. So that's what's happening in our area. In New York area, land is sinking because the earth is adjusting to the last ice age. And part of Canada is now uplifting, so our area in northeast of the US is sinking. I don't get it too much into the details. So now we know relative sea level rise is different from global sea level rise. On this map, what we see is projections of relative sea level rise for the end of 21st century under the high emission, or just summarize it, under the worst case scenario. So the global mean sea level rise is 2.5 feet, but it's obvious that along the US coast, the relative sea level rise can be significantly different from this global sea level rise. For example, in New York City, by the end of 21st century, under this worst case scenario, we get 3.4 feet of sea level rise with 50% exceedance probability. So the point here is that relative sea level rise really depends on the region. And it can be higher than global sea level rise, for example, in our region, in New York City area, or lower than global sea level rise, for example, in northwest of the US. You see here, this area in Oregon and Washington State, the circles by yellow, they mean a sea level rise of between 0 and 1.64, which is much smaller than the global mean sea level rise. And that's again because of the local effects, which are different in our region than northwest of the US. With that, we want to focus now on our area. relative sea level rise at the Battery, New York. These results, again, are from the Intergovernmental Panel on Climate Change. So they projected sea level rise at the location of the NOAA tide gauge at the Battery, New York. Again, here we are looking at the best case scenario, 0 CO2 emissions around the middle of century. With 50% chance by the end of this century, we're going to have a sea level rise of 1.1 feet. How much was the global sea level rise? 1.3 feet. So obviously, we have a larger problem when we compare ourselves with the global mean sea level rise. And with, I would say, with 98% confidence, I can say that the sea level, relative sea level rise is going to be between 0.2 feet and 4.4 feet. But with 50% chance, it's going to be 1.9 feet of sea level rise by the end of 21st century under this optimistic climate scenario. What about the worst case scenario? SSP 58.5 scenario, which is high reference scenario with no additional climate policy. Without any climate policy, this is what we'll get in the future. With 50% chance, we're going to have 3.4 feet of sea level rise at the location of the Battery tide gauge. Compare that with the global sea level rise, which is 2.5 feet. Again, relative sea level rise in our region is much higher than the global sea level rise. And then if I look at the range, by the end of this century, this relative sea level rise at the Battery is going to be between 1.9 feet and 6.9 feet. Again, a large range. Why? Because of uncertainties in the future. Now, the question is that, so we know these projections of sea level rise. What do they mean in terms of flooding, high tide flooding? What would happen to high tide flooding in Jamaica Bay? So I got this figure from this map from New York City Flood Hazard Mapper. So you can refer to this website to get the same maps. This map here shows the extent of high tide flooding in the current decade, in the 2020s, in Jamaica Bay flood, around in New York City area. We are looking at 2020s. What about the end of 21st century? Here on the right side, I have the figure for high tide flooding at the end of this century. And obviously, the extent of flooding has significantly increased, especially in some areas. For example, the Rockaway Peninsula, a large area is going to be flooded by high tides, or in Coney Islands and other neighborhoods in Canarsie. So let's focus maybe on one area. Let's focus on this region, this area, Coney Island and other neighborhoods. Let me zoom in on this area. So this is what we'll get by the end of 21st century in terms of high tide flooding. What these colors are, I can see dark pink, light pink, different strange, different colors. So if we focus only on light pink here on this legend here, it says high estimate, 75 inches of sea level rise, about 5 feet something sea level rise. Under that case, under that scenario, you see how the area of area which is flooded by high tides is significantly wider than when we consider a low estimate of sea level rise, for example, 15 inch, which is represented by dark pink. So it means that it really matters how much sea level rise we'll get in the future. It can significantly change the area of high tide flooding in this neighborhood. Or another neighborhood, if we focus, is Canarsie. If I zoom in, again, I see large neighborhoods, large areas of Canarsie will be flooded by high tides twice a day under the worst case scenario of sea level rise. And keep in mind that these maps are assuming that there won't be any mitigation effort. For example, no seawalls or no levees. So these are just under the present day conditions. What about the combined effects of sea level rise and tropical cyclones on extreme water levels? Those maps which we saw in the previous slides, they just focused on sea level rise. But we have bigger problem, right? We have tropical cyclones. We have a storm surge. Then what happens if I add a storm surge to sea level rise? The impact is going to be significant. So let's look at the impact of climate change on flood hazards in Jamaica Bay. Before doing that, I'd like to have your attention to this definition here, annual exceedance probability, which is the probability that a given water level will be exceeded in any 1 year. For example, here this figure on the x-axis, I have annual exceedance probability, which I defined it here in this line. On the y-axis, I have extreme water level in feet. For example, under a 1% annual exceedance probability, the flood level, it's going to be about, I would say maybe 5 feet. So it means that there is 1% chance in every given year to have a flood level of 5 feet or higher. 1% chance in every given year. This curve here represents water levels for the late 20th century in Jamaica Bay. What would happen in the future, let's say in mid-21st century, how this curve would change? If I look at the mid-21st century, under high emission scenario, I get this blue line. Ignore the shaded area. It's the statistical uncertainty. We don't get into details, just let's focus on the solid lines. Let's again focus on 1% chance. So we said that under late 20th century, 1% exceedance probability has a corresponding water level of 5 feet. What would be that under future or under mid-21st century? So if I just intersect this blue curve, I can read the water level, it's about 7 feet. So if during historical period of late 21st century, if a water level of 5 feet had 1% chance to occur every year, now that water level is 7 feet, or not now in the mid-21st century. What about late 21st century? The situation gets worse. We have 1% chance in every given year to get a water level of about, how much is that? About maybe 10 feet every year. And I think I have a table here. All right. So in this table, we have time versus water level with 1% chance to occur. Compare these numbers. Late 20th century, we have 1% chance of a storm-induced water level of 5.34 feet or higher. Mid-21st century, that number changes to 6.8 feet. And late 21st century, that number changes to 10.3 feet. Keep in mind that this figure was generated based on the effects of both sea level rise and tropical cyclones climatology change. So we have the effects of both sea level rise and tropical cyclones. Now I want to look at the flood maps. So I have about, I think, 8 more minutes or 5 more minutes. Now I'm going to look at the flood maps in Jamaica Bay. For this specific storm, I'm going to see how future sea level rise and future storms would impact the extent of flooding in Jamaica Bay. I'm going to look at one scenario, a Category 1 hurricane which makes landfall on the Rockaway Peninsula. Under no sea level rise, this synthetic hurricane generates a water level of 8.6 feet above the present day mean sea level in Jamaica Bay. Now we are going to see how the extent of flooding would look like under no sea level rise and with sea level rise scenario. Here is the map I get. I have two colors here, dark blue and light blue. Dark blue represents the area which will be flooded under no sea level rise, and light blue is the area which will be flooded under a 5.1 feet of sea level rise. And it's obvious that the extent of flooding would increase substantially when we add sea level rise. So we talked about sea level rise, we talked about tropical cyclones or storm surge. What about wind generated waves? Are they also important? Should we also look at waves, or we just let's just focus on storm surge and sea level rise? So what we did in our group, we used our models to simulate waves under different sea level rise scenarios. We wanted to see how waves look like in the future in Jamaica Bay. Are they going to be bigger, and how much bigger? So sea level rise means deeper water in the bay, which results in larger waves. Why larger waves? Because waves lose more energy in shallower water, and the process is called depth-induced wave breaking. Because of sea level rise, the shallow areas of Jamaica Bay, they're going to be deeper. And then what it means? It means that waves, we expect larger waves because of deeper water. So we use our model to simulate wave height in Jamaica Bay for that synthetic hurricane, which I showed you in the previous slide. That hurricane makes landfall on Rockaway Peninsula. For that specific storm, we get this peak wave height in Jamaica Bay. By peak wave height, I mean the maximum wave height during that specific storm. The warmer color means larger wave, the cooler color means smaller wave. And it's obvious that in areas which are currently deep, we get larger waves. For example, in Grassy Bay, Grassy Bay is deep. So we get larger waves in Grassy Bay represented by red color. Whereas in the center of the bay, we get blue color, which means smaller waves, or green color, which means smaller waves. But around the perimeter of the bay, which we have the deep channels, we also get larger waves, represented by yellow color and red color. Now, what about if I add sea level rise to my model and simulate this hurricane again? Now I'm going to show you the wave height for the same storm, but with 5 feet of sea level rise. Now I get a larger area of the bay covered by red color, which means larger waves in larger area of the bay. For example, in Grassy Bay and even in the center of the bay, the color has changed from blue, for example, to yellow, which means an increase. So blue represents, for example, 1.6 feet of wave height. Yellow represents 3 feet of wave height. So it's obvious we'll get larger waves when we have sea level rise. So what? Waves getting larger, are they important, or we should just focus on storm surge and sea level rise? So larger waves mean more intense shoreline erosion, flooding due to wave overtopping, and damage to boats and structures. Some examples are shown here, and some other impacts. So the point is that we should also pay attention to waves during storms, during extreme events. The waves can be larger due to deeper water in the bay as a result of sea level rise. I think we are almost done, and I'd like to thank everyone for your attention, and I'd be happy to ask any questions from the audience.
I can I be heard, Reza? Reza?
Yes. Yes.
Ah, okay. Okay. So I think let's see. Are there questions for Reza on this? Um, there there is something. There's a question on will sea level rise impact Jamaica Bay's wetlands? Will they drown, or is marsh migration inland possible?
Uh, as far as I know, so Jamaica Bay, the sediment budget in Jamaica Bay is low. It means that naturally salt marshes, they can migrate upward due to sea level rise. Sea level rise brings sediment, and these marshes can migrate upward, or they can migrate inland if there is a space. But in Jamaica Bay, I don't know how much space we have on land for marshes to migrate. But in terms of migrating upward vertically, it really depends how much sediment exists in Jamaica Bay. If there are enough sediment in Jamaica Bay, then sea level rise, then salt marshes can adapt to sea level rise. Their elevation can increase vertically because they can trap more sediment. But if there are not enough sediment in Jamaica Bay, then the marshes are going to disappear, because if they cannot migrate upland, then they cannot migrate vertically. Unfortunately, they will disappear.
Okay. Reza, that presentation was so clear, but also so frightening. and I think that that I guess I didn't realize that I was we were being too optimistic, or when we were talking about only sea level rise, when you have, as you have well pointed out, there's cyclones, tropical cyclones, and there's wave heights. And that would have made the title of our conference too long, but you really did us very well and set us for the afternoon's discussions, which will be, okay, we've seen the Bay today, we've seen the communities today. Now you've given us a look at what's going to happen towards the end of the century, and this afternoon's discussions will be responses and reactions to that. And so again, to everyone, I'd like you to realize that at 3 o'clock we have, you know, an open, wide open discussion. We will have a break now until 1:15. You could go, please come back. We will have first Nathan Kensinger is going to talk about his paper, and then we have a panel that will be discussing various issues connected with what Reza has just laid out for us. And so, Reza, thank you very much. I really appreciate it. And for sure, please.
Unfortunately, I won't be able to join the afternoon session. If anyone has questions, please email me, and I'd be happy to answer questions through email. If you go to the Department of Civil Environmental Ocean Engineering at Stevens, you can find my email, or perhaps reach out.
Okay. Someone, one of our administrators will put your email in the chat, Reza.
I just put it there in the chat.
Oh, okay.
I'd be happy to answer any questions. Thanks.
Thank you very much for that. And again, thank you for your presentation. And now we'll have a transition. What we will be doing is we'll be seeing another film during the break. We have Nathan Kensinger's film that he directed and produced called Managed Retreat. And then we will show a montage of photographs of our colleague, Robin Michaels. I should say to the audience that we have working with us on this conference today, two photographers, Nathan Kensinger and Robin Michaels, and they are the photographers of the Brooklyn waterfront, whether it is the changing levels of the sea along the waterfront, whether it's the changing development along the waterfront, whether it's historical changes that have occurred. They have been the chroniclers of that. And so we are very pleased to have them. And once again, Reza, thank you very much. And now if my staff can move, here we go.